So simulated annealing is another kind of algorithm which is an iterative algorithm. Here, unlike genetic algorithm where the concept was taken from evolution or genetics or the living examples, we try to incorporate the example coming from physics or probably thermodynamics or metal industry, where they try to take those metals and then they try to increase the temperature so that the whole metal is then gets melted, and then in the molten state they take that metals and then they cool them gradually, and then they have different, for example, costs where they can take those metals and get different shapes. And the key to having a successful annealing is that the temperature should be lowered gradually. So the system is stable where the temperature is the low, but initially you have to increase your temperature very high and you gradually cool down. While you are cooling your metal, there comes some points which we call it as critical points, where if your temperature change is not continuous, it's a drastic change or it's an abrupt change, your metal can get some other shape which you are not interested in. So these kind of concepts are also implemented in this multiple sequence alignment problems. Let's see how they go over here. So again, it's a heuristic approach, and it's kind of a generalization of Monte Carlo methods. Monte Carlo methods are kind of finding global minima of a function in a combinatorial problem. So you can come up with many solutions of your problems, and then you try to get which one is the best one. So let me take this slide to tell you what is the local minima or what is the global minima. So here on the x-axis we have different states of, for example, your metal or your system, and then on the y-axis you have energy. So here lower energy is the best. So the shape is stable where we have some lower energy state. So we start with the high energy state as we see here, and we gradually keep on decreasing our temperature. So here, for example, the temperature is low, and then system passes through a space where again you have some high temperature peak. So you have your peaks and valleys, and again you see a valley over here, you see a peak over here, again there is a deep valley over here. So that is the place where the system should go starting from here. So what happens is, what is the local minima? So local minima is you achieve a minima which you feel like that is your final destination, but actually it's not. So you are taking your metal or you are solving your problem and you come up with a solution and you find that is the best solution. That's it. Maybe this solution may not be the right solution. So if you are feeling like that is the right solution, you're kind of stuck in local minima. So if your metal is being cooled and there comes a stage where it tries to form a shape, and if you stop it over here, that is not the exact shape which you want. So what you need to do over here is then you probably need to raise the temperature again so that it should get out of this local minima and try going to its final destination, which was the global minima. So that is the overall trick or philosophy behind these simulated annealing problems. So we come up with some solutions, we try to find out the real-time big solution, which is in this example our objective, that is in order to find the global minima. So that is our objective. So what we do is, if we are stuck with local minima, we try to kind of shuffle our sequences, we try to break those alignments and start realigning our sequences again, unless we come up with the final best alignment. So if you are following this kind of approach, you are actually following a simulated annealing approach, and this approach is then embedded or implemented in the algorithms that are working for multiple sequence alignment. So there is one algorithm or one software, we call it as MSA, multiple sequence alignment by simulated annealing. So that is the example where this has been implemented in multiple sequence alignment. So let's take those steps one more time and put them together in these points. So following elements must be provided in simulated annealing. There is a solution space for two sequences with length n and m. The maximum length of an alignment is equal to m. So I mean the alignment should not exceed the lengths of the individual sequences. And then we need to have a generator of random changes in the solutions. You get your solutions, and then there are some system that can generate some random changes in your solutions. So it can introduce random changes and allow all possible solutions to be reached. And there is another thing that is there in its scoring, or we call it as a CAO, contact accepted mutation scoring matrix. It's another matrix that takes into account the amino acid interactions. So amino acids, they interact with one another, and that interaction, then that information is embedded into this kind of matrix. So CAO scores can be used to detect both sequence as well as the structure similarities. It serves an intermediate between sequence-based scoring and structure-based scoring methods. And this matrix is actually 400 by 400, since we are taking 20 amino acids and we are having all their possible contacts. So 20 by 20 on one side, which is equal to 400, and 400 on the other side. So how different amino acids, they contact with one another, so that is their structures are then formed. So we are kind of doing those multiple sequence alignment, but we are taking into account what will be the final structure of that protein. Mainly these kind of approaches you will go and read in your the structure prediction course or protein structure prediction problems. The score is overall sum of the sequence scores plus the score which we are getting from this contact matrix. So that is, there are two kinds of scores for assessing the quality of an alignment: the sequence scores and the contact scores. The scoring function is present down below. We see that it is combination of the score from sequence as well as a weighted score coming from those contact information where we have embedded this contact matrix. There are other parameters. So relative weight of CAO score versus Blossom matrix, that is this W over here, and C is the matrix constant for CAO score. So in addition to that, there are gap penalties, which are gap open penalties like P, gap extension penalty like Q, and contact penalty like R. They are also embedded in these scores. We also need an annealing schedule for this algorithm, so an initial temperature and rules for lowering it as the search progresses. We also need a termination criteria, an algorithm that halts when the solution is not changed in 3 generations searching. So where we should stop, what is our final solution? So we need a termination criteria for that. So we see in this section that this simulated annealing is a generalization of Monte Carlo methods, and it can be used to find the global minima of a function in combinatorial optimization problems where you can have combination of different solutions.